Next up is, our next speaker is Francesca Parisi from Cornell University. She's working on a project that's led by Asu Özdağlar at MIT, and it's titled Optimal Adaptive Testing for Epidemic Control, Combining Molecular and Serology Tests.
Perfect. Thank you so much for the introduction. So let me start by saying that this is a joint work together with Aron Asimoglu, Alireza Falla, Daniel Hatterlock, Asuman Özdağlar, and Sarat Patil from MIT, and myself and Andrea Giometto from Cornell University. And actually both Asu and Andrea are on the call, so you can also direct questions to them. So let me start with a motivation for this talk, which comes from the observation that, as highlighted by COVID, non-medical interventions are actually a fundamental tool for epidemic control, especially in the initial phases of an epidemic. And among non-medical intervention, actually testing and isolation prove very effective, as highlighted by countries such as South Korea, Taiwan, or Germany, or on a smaller scale by university campuses. And we heard even today some high-frequency testing policies that led to very successful control of epidemic spread. Now, one of the downside, however, of testing is that these policies are typically very expensive and they are subject to supply constraint and logistical difficulties, which means that they are a scarce resource. Now, despite this, however, there's been relatively little theoretical work on how can we actually optimally allocate such a scarce resource to control an epidemic. So while previous work looked, for example, at trade-off between testing frequency and testing sensitivity, or how can we relax some lockdown policies based on testing information, our core objective here is to try to understand actually what is the optimal testing frequency. So how often should we test people in order to control an epidemic? And in particular, what we want to compare are advantages and disadvantages of adaptive testing policies, where we change the frequency based on the epidemic state, with respect to constant testing policies where the frequencies is the same, which has been the standard for COVID-19. And in order to do that, we're actually going to consider two different types of testings. So we're going to consider molecular testing. In the case of COVID-19, that would be PCR testing, which I'm sure every one of you is familiar, which give information about current infection. And I'm going to argue that molecular testing are, of course, fundamental to detect and isolate active cases. And so these are really important for control. On the other hand, however, there is also a second class of testing, which is called serology testing, which actually gives us information about antibodies that are produced as a consequence of an infection, and therefore give information about past and previous infections. And what I'm going to argue in the talk today is that this other class of testing is also relevant, and in particular, it's important for understanding what is the aggregate state of my epidemic. So what is the epidemic state? And so the main contribution of the work that I'm going to present today is that we will focus on a classic SIR model. And within this model, we're going to look at what is the optimal molecular testing rate for control. And again, here we're going to use molecular testing because we want to make sure to isolate active cases to prevent them for further spreading the infection. And one key result that I'm going to show is that the optimal testing rate is actually adaptive and depends on the epidemic state. So the second main thing that we're going to look is whether the policymaker can actually estimate this epidemic state from available data. And I'm going to argue that for that, serology testing becomes really useful. And so the kind of general picture that I want you to remember is this picture here. So we're going to have both molecular testing and serology testing. And the idea is we're going to use serology testing to be able to estimate the state of the epidemic. And then we're going to use the estimated state in order to design the optimal molecular testing in order to control the epidemic. And I'm also going to show you how we can validate the proposed approach with a stochastic epidemic model. Okay, so to start with, let me actually present the SIR model. I mean, we have already heard this a little bit today, but just to make sure everybody's in the same framework, what we're going to focus here is a SIR model. So again, as a caveat, this is not a model suited for COVID-19. So what we wanted to use is a core epidemic model, which can then be tuned to different diseases. And so in this model, we have that the population is divided into three compartments: susceptible, infected, and recover. And from now on, the letter S, I, and R are going to denote the fraction of agents that we have in each one of these compartments. And the dynamics of the SIR model, we have that susceptible individual may become infected because of interaction with infected individuals. And this will happen with a rate, which is given by beta I, where beta is the so-called transmission rate and is related to how many contacts a susceptible person has on a given day. And one thing that I want to stress is that this parameter here may actually be time varying, because again, it depends on people's behavior, which may change depending, for example, on policies or other adaptation of the current state. And then once agents are infected, they can transition to the recovered state, and they're going to do that with a rate gamma, which is 1 over the typical duration of the illness. And so this is the classic SIR model. Of course, if we want to understand optimal testing rate, the first thing that we need to do is we need to introduce testing. And so the way we do this in our model is by partitioning the infected compartment that I've just described into 2 different components. So we're going to have infected undetected agents and infected detected agents. And the idea is that testing allows us basically to move agents from undetected to detected. And we are going to do that with a rate, which is this eta times theta, where eta is the sensitivity of our test, so how effective this test is in actually detecting. And theta is actually the testing rate. And you see that we made this parameter now time varying because we want to study adaptive policies. And so this is going to be our control variable. So what we can change in order to actually try to contain this epidemic. And so really what we want to understand from this model is how should we design this theta parameter. And actually, our objective will be to minimize the overall testing needs that we need to control the epidemic, which is here quantified by the integral over the entire horizon of the testing rate. And of course, we want to minimize testing while being able to contain the epidemic. And in a first moment, the way I'm going to quantify this objective is to ask that the number of infected undetected agents should be less than a threshold, which is decided by the policymaker. And the reason why we want to constrain infected undetected agent is because there are agents that are free to circulate, so they may infect others. And moreover, if an agent is undetected for a long time, it has higher chance to develop the complex symptoms that will require hospitalization. So our first contribution is to actually solve this optimal control problem. And what we show is that the solution is indeed time varying, and it's actually quite intuitive, and it's depicted here. So you see what's going to happen is that you have in blue here the infected undetected as a function of time. And we have an initial phase of the optimal control where the infected undetected is below the desired threshold when we actually do not do any intervention. And then the moment the infected undetected agents reach the threshold, the desired threshold of Emax, then we start our testing protocol. And we actually do that in an adaptive way in order to maintain the infected undetected agent at the desired threshold. And you can actually compute pretty easily what is the testing rate that you need to do that by just equating the derivative of the infected undetected to 0. You see immediately you can derive what is the testing rate that you need. And one thing that I want to stress is that this is a closed form expression that depends on the epidemic state, and in particular depends on the number of susceptible agents. And since in an SIR model, the number of susceptible agents is decreasing, you see that the testing that you need is actually decreasing in time until you reach a certain point where actually this is the so-called herd immunity point where you don't need any intervention and the number of infected will naturally decrease. And the way we prove this result is by using a theory of the most rapid approach path. So the idea is that the only way you can stop the intervention is if you reach herd immunity, so this state here. And so the optimal control should actually try to reach this point as fast as possible, and this is the trajectory that achieves that objective. And as I mentioned here, we model the epidemic constraint requiring that the undetected should be less than the threshold. In a more general model, you can actually require that the total number of infected, so both undetected and detected, should be less than the threshold. And you can actually also impose some upper bound on the daily testing rate. And I'm not going to go to the details of this, but what we show is that the core intuition remains the same. So again, you want to adapt your testing rate in order to maintain the constrained quantity, so the total number of infected in this case, to the threshold until you reach a point where infection naturally decreases. And if you look at the control that achieves that, you'll see that it's slightly more complicated than before. We have these two peaks of maximum control. And the technical reason for that is that the constrained quantity here has a derivative that does not depend directly on the control. And that's the reason why you need to actually start controlling a little bit before reaching the threshold to make sure that you reach on a tangential way, so that then you can actually make sure you will not overshoot. And one point that I want to make is, however, even in this more complicated policy, we can compute analytically what are the optimal switching time as a function of the state, and in particular, the number of susceptible agents. So overall, the take-home message from this part is that the optimal testing policies is adaptive and depends on the epidemic state. And that's actually what leads us to the second part of our analysis. And this is from the observation that in reality, the policymaker does not know the epidemic state, so he needs to infer this from data, and the data that's available is detected cases. So the first question that we ask is, are these detected cases from molecular testing enough to actually be able to recover what is the underlying epidemic state? And the answer that we have is that is negative, in the sense that when the transmission rate is time varying, actually, this is not always the case. So measurements of detected active cases may not be enough to recover the state. And the way we prove this is in a constructive way by actually constructing two different systems that start from different initial conditions. They have different transmission rate, but they actually lead to exactly the same observable output. So what this means is that if I observe that output, I cannot distinguish between these two systems. And I'm not going to go to the mathematics of this, but I kind of want to give you a little bit of an intuition of what the problem may be with molecular testing. And really the idea for that is, remember, molecular testing detects active cases. And agents are active over a very short window of time, which is either 2 or 3 weeks. So if you have testing that is not that frequent, what may happen is that you entirely miss one case by doing molecular testing, and that kind of cause problem for state estimation. On the other hand, at the beginning of this talk, I mentioned there is another class of testing, which is serology testing, which instead is typically less sensitive, but gives information about the entire history, so also about previous infection. Then you see detectability windows, therefore much longer with serology testing. And that's why we thought this serology testing could actually be very well suited for state estimation. And in order to kind of prove this point, what we did was to encode serology testing in our previous model by allowing a constant testing rate theta b, which is of serology. And one thing that I want to stress is that serology testing is structurally very different from molecular testing, because again, does not only gives information about active cases, but also about past infection. And to encode that, we split the recover state also in recover undetected and recover detected. And so recover undetected agents will be agents that had the infection in the past, but they were never diagnosed. So the policymaker does not know that they have immunity. When instead the recover detected cases will be agents that had the infection in the past, and they were either detected while they had the infection, maybe from molecular testing, or they are detected afterwards because of serology. And so what we show is that with this addition of serology testing, we actually have that our system becomes observable, which means that if we record both detected cases, detected active cases, and detected past cases, then we can indeed estimate the state of our epidemic. And one important thing that I want to stress is that this is a structural property, which means that it does not depend on the level of sensitivity of serology, nor actually on the testing frequency that we use for serology. Of course, however, a caveat is that this observability concept is a priori observability, which means that it works when we have perfect measurements with no noise in continuous time. While in practice, however, there's going to be a number of known idealities. And in order to test against these known idealities, what we did was to simulate number of detected cases by using a stochastic continuous time Markov chain model, capturing the fact that typically infection and recovery events are actually stochastic events. And then what we did is also assume that we cannot observe continuously a number of detected cases, but we're going to do that discretely in time, so maybe every day. And so in order to actually recover the state, what we need is to build a state observer. And what we actually built in this case was an extended Kalman filter with state constraint. And one important aspect of the Kalman filter is that you need to specify what is the process noise, so what is the mismatch between the model, which in our case is the stochastic model, and the model used by the Kalman filter, which in our case was the SIR deterministic model. And so in order to understand this mismatch and describe this process noise, what we did was to derive a Langevin approximation of the stochastic epidemic dynamics, whose mean is actually equivalent to the deterministic model that we use for our control analysis, and whose variance we can actually compute explicitly in terms of the epidemic state and the number of agents. And so by feeding this information to the Kalman filter, we are able to optimally incorporate observations. And so to conclude, let me just show you some simulations. So what you see here is one simulation from this stochastic model. And what you see in red here is the total number of infected. And in black here is the estimate from the Kalman filter. So the first thing that you should observe is that indeed the Kalman filter is able to recover the state. And then the other thing is that we use this estimated state in order to implement the testing, the adaptive testing policies that I've described before. And you see that indeed with that, we are able to control the total number of infected to the desired threshold, which is here in yellow, of course, with some fluctuation because this is a stochastic model. One thing that I want to stress, however, is that these fluctuations are something that we know how to quantify because of our analysis with the Langevin approximation. And so if you actually repeat these replicates, you'll see that on average, the mean of all these replicates indeed really follows the desired threshold of Imax. So basically, to summarize from this simulation, what we observe is that we can successfully contain the epidemic at the desired threshold. And actually, what we also notice is that we can reduce the cost with this adaptive testing process of up to 60%, at least for the parameters that we tested, with respect to instead constant testing approaches, which would just use the same frequency of testing throughout the epidemic. Okay, so to conclude, basically what we did here was to look at optimal testing strategy in an SIR model. And we had two main insights. First of all, we were able to characterize what is the optimal molecular testing strategy. And we showed that this takes a very simple form, similar to a most rapid approach path, which is adaptive and depend on the state of the epidemic. And then we show how serology testing can be used to actually estimate this state. And I want to conclude just with a few caveats. Of course, whenever we claim optimality, here is in the context of the model of the epidemic constraint that we formulated, which is just keeping the number of infections below Imax. So that's kind of a containment type of strategy. Of course, there's an entire other class of strategy, which is suppression, and which one is to be preferred is a choice of the policymaker. And we also, again, derive our results for a standard SIR model. So this is not directly applicable to COVID-19, but I think some of the insight can be applied to these more complex compartmental models. And here we model stochasticity coming from extrinsic stochasticity of infection and recovery events, but of course there are many other sources of stochasticity. So I think overall what our theoretical analysis provides are some information about choices of candidate policies that of course then needs to be tested extensively with ensemble models before being applied to practice. Okay, so thank you so much and happy to answer any question.
Thank you, Francesca. We have time maybe for a question. Shrikant?
I don't know if other people have a question. I'll wait. I don't know if anybody else. Okay, if not, I'll go ahead. Oh, good. Prashant, go ahead. Go ahead. Sorry. Yeah.
That's right. Thank you. Can you comment upon the observability test that you used for the observability result?
That was actually a constructive way because we, let me go back to that. So basically, in the first case, when we just had molecular testing, here, what we did was really just construct two systems and show that if they start with different initial condition and we apply different time varying parameter, and that's actually very important. If you have constant beta, then it is observable. But if you allow for different time varying beta, which may be the case if people change behavior, then you actually have exactly the same output from these two systems, but their underlying state is different. So that was a very constructive approach. And then instead, to prove again that if we add serology, then we have that the system is observable, you can actually verify that directly from the equations. Let me go back. Let's not go back.
Okay, yeah. You can't see the slides if you're trying to show your slides.
Oh, I'm sorry. Okay, then let me just say it. So we can verify that directly from the equation, because if you have information about detected, infected, and detected recovered, just from the equation, you know that you have information about the derivatives, because in observability, you start that in continuous time, and you can solve the equation for the unknowns, basically. That's all it is. Basically, you'll get a system of equation with 3 unknowns, and you can solve it.
Thank you.
Is there time for one more question, Larry? Or?
Sure. Yeah.
Quick question. So I don't know if you may have already touched upon it, but I didn't. Maybe I might have missed it. But feedback often provides robustness. I mean, do you observe anything like that? Like if the parameters are varying or estimated incorrectly, is your testing strategy more robust than not using feedback?
I did not test that directly, in the sense that we only implemented the feedback one, and I can tell you that's very robust. One thing that we checked, for example, is what if some of these parameters are time varying because of seasonality, maybe and then what we verify is that indeed our estimation can capture that. So we will be able to track the changes in the parameters and react to that. So and I think a big part of that and the stability of that is because this is a closed loop policy that reacts based on the states. So that's a big advantage. Yeah.
Okay, thanks.